Okay, this is the Intro Chem review session, review day for final exam. These are the problems for Monday. If you are an online student, this packet is posted on the course website for you to download and do on your own time. You can watch the video after you've converted and after you've done all the problems for yourself. Obviously, you guys here on campus, I gave you a hard copy of this. Now, my disclaimer is what? Just because it isn't in this packet, does that mean it's not on the final? No. How do you know what's on the final? Where do you go to get the information? It's on the course page. There's a handout called Final Exam Outline. Okay, so make sure you go check that out. All right, let's do the problems for Monday. Full electron configuration for calcium. Calcium is 20 electrons, right? I said full, so that means I can't use the shortcut. Good news is I've only got 20 electrons to deal with. All right, so if I'm using the periodic table or the diagonal rule, either way, should give me calcium. Do we agree? Any questions on number one? All right, let's do the noble gas configurations for cobalt and tellurium. So cobalt is element number 27. It's in the D block. Is this one of the exceptions? No, it's not, right? What are my exceptions, just for review? There are 4 in the D block that you're responsible for. Chromium, and there's another one in the 4th period, chromium and copper, and then directly under chromium we have molybdenum and silver, right? Those are the 4 you're responsible for. Cobalt's not one of them, so we just write normal electron configuration. Since we're using the shortcut, what element goes in brackets? Argon, and then all I'm responsible for are the leftovers, right? So, because this is chromium, we're in period 4, so that's 4s2, 3d, 1, 2, 3, 4, okay. Or we're going to cobalt, 1, 2, 3, 4, 5, 6, 7. Do we agree? So how do you know to do the shortcut method? Because I said write the noble gas. That's the shortcut. And tellurium. Tellurium is element number 52. Okay, so using the shortcut notation, what element goes in brackets there? What do we have in brackets for tellurium? Number 52. Krypton. And then all I need to write are the leftovers. So tellurium's in period 5, so that'd be 5s2, 4d10, 5p, 1, 2, 3, 4. Yes. Do we agree? Remember, these are our valence electrons, these are our core. These are our valence, these are our core. Okay, questions on number 1 or number 2? All right, let's do number 3 and 4. Slide everything up a little bit. Okay. Okay, 2.5 liters. Let's do some conversions. 2.5 liters to milliliters. So, what goes on bottom, liters or milliliters? Liters. And milliliters goes on top. How many milliliters are in a liter? 10 to the 3rd or 1,000, right? So we're taking 2.5, multiplying it by 10 to the 3rd. So that's just what? 2.5 times 10 to the 3rd, right? Because liters cancel, I'm left with milliliters. Do we agree? Just setting up a conversion factor. Let's do liters to, what does that funny looking symbol right here mean? It's the Greek letter mu. What's this funny looking symbol? Greek letter mu. What prefix does it stand for? Who remembers? This is milli. What's this one? This is micro. So if you've forgotten your prefixes and the numbers that go along with them, you need to review that, right? 1 liter is equal to how many microliters? 10 to the 6th, right? So 2.5 times 10 to the 6th is just 2.5 times 10 to the 6th. Do we agree? And then for C, 2.5 liters. What does K stand for? Kilo. 1 liter is equal to how many kiloliters? 10 to the negative 3rd. If you don't like that, that's the same thing as 0.001. Right? So that's just 2.5 times 10 to the negative 3rd kiloliters. Do we agree on number 3? Conversion factors. Any questions on number 3? Questions on 3. Make sure you relearn your prefixes. You have to know those prefixes, right? Otherwise, that will be very challenging. Okay, values of N and L. Let's review our quantum numbers. S, P, D, F has values of 0, 1, 2, and 3 for L, right? And N, what does N refer to? N is size, right? And L is shape. So if it's 3P, that means N equals what? 3. And L equals what? 1. Do we agree? For 1S, N equals 1 and L equals 0. And for 4D, N equals what? 4. And L equals 2. So the main thing here is you need to review this thing, right? That was back from the beginning of the semester. We did quantum model in like week 2, week 3. Okay, number 5. What are isotopes? How can you tell if two atoms are isotopes? So what are isotopes? What's the definition? They have to be atoms. What? Can they be different elements? No. Atoms of same element. Right. With different number of what? Neutrons. And we denote neutrons as N with a 0, right? And then how can you tell? If two atoms are isotopes, what will be the same? They'll have the same atomic number, right? What will they have that's different? Mass number, right? Right, because atomic number is just number of protons, whereas mass number is what? It's protons plus what? Neutrons. And if this number is different, that's what makes the mass number different, right? So think about carbon 11 versus carbon 12 versus carbon 13 versus carbon 14, right? Different number of neutrons, but they're all carbon. They're all carbon. So if you're looking at nuclear symbols, we have nuclear symbols. Let's just say I give you X and Y. And I say, okay, and I ask, are those isotopes? Would your answer be yes or no? Are X and Y isotopes here? Yes, they are, because they have the same atomic number. What if I gave you this and asked, are these isotopes? No, right? They have different atomic numbers. They have to be the same element, right? They have to be the same element, which means they have to have the same number of protons. If you change the number of protons, remember we talked about this, that's like changing your social security number, right? If you change your social security number, you're a new identity. You're a new person. That's illegal, right? That gets you in big trouble. If you change the mass number, that's just like gaining weight, right? That's not illegal. That's not going to make you file your taxes differently. You're not assuming a new identity if you gain or lose weight. You are assuming a new identity if you change your social security number. Any questions on 5? Questions on 5? Okay. Let's move everything up. Look at. What does an orbital represent in the quantum mechanical model of the atom? What is an orbital? Area, yes, where it's, say that again? Right, most likely to find an electron. Right, if I said, okay, what's the probability of finding a cow in this room? Virtually 0, right? If we say, okay, let's go to a farm, what's the probability of finding a cow there? Pretty high, right? So we draw a circle around where all the cows are hanging out. That would be the orbital, right? Our orbital here would be 0. There would be no orbital because there's no probability of finding a cow in this room. Okay, let's talk about number 7, 2p versus 5p. So how are they different? How are they similar? They have the same what? Same shape. What's the difference? Right, different size. Size. All right, so if we're drawing these, I didn't really give myself enough room. How am I going to denote the difference in size? How will I denote that difference in size? Tick marks, right? So 2p versus 5p, could I draw those on the same set of axes? Yeah, you could. And you could draw it along the x, the y, or the z. Whatever makes you happy. I don't care if you draw it going this way, or going diagonally. It makes no difference to me, as long as you've got the right tick marks to show size. Right, so let's just, for fun, draw a diagonal. P shape looks like a figure 8, right? There's 2p, 1, 2, 3, 4, 5, 3, 4, 5. And there's 5p, right? There's 2p, 2pz to be specific, and there's 5p. Yes? The only difference is size. Higher probability of finding an electron in the bigger one, right? Just like my probability of hitting the dartboard is higher if I'm shooting at a big dartboard versus a little one. All right. Any questions on 6 or 7? Let's move on to number 8, some sig fig calculations, which are always problematic. So does my calculator know anything about sig figs? Is my calculator smart enough to be able to do that? No, I have to know the sig fig rules, right? So what's the rule for addition and subtraction? Least number of decimal places, right? So 7.939 plus 6.26. My calculator spits out 14.199. Can I keep all those decimal places? No, I have to round it to how many decimal places? 2 decimal places. So what does that round to? 14.20, right? This 0 is significant because of the decimal place, right? Now, I didn't give you units. If this was milliliters and milliliters, then obviously your unit would be milliliters too, right? All right, let's do this one. 2.4 minus 8.321. My calculator tells me negative 5.921, because my calculator's dumb. It doesn't know anything about sig figs. How many significant figures can I, well, how many decimal places, I should say? How many sig figs total, or number of decimal places? 1 decimal place, 2 total sig figs, right? So how would I round that? Negative 5.9, right? Again, if I had given you units, if this, for instance, said grams and this said grams, then obviously my answer here would also say grams. Make sure you carry through any units that you're given. And then for the last one, 2.333 plus 1.56 minus 0.29. My calculator spits out 3.603. How many decimal places can I keep? 3 decimal places, 2 decimal places, 2 decimal places. So I can only keep 2 decimal places. So that would be 3.60. If I had given you meters, 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 obviously your answer would also have meters as well. Any questions on 8? Okay, number 9, we're going from kilograms to milligrams. Can I do that in one calculation? No, we should do what first? I advise going kilograms to grams and then grams to milligrams, right? Do that in 2 calculations. So there's step 1, there's step 2. So 42 kilograms. So we've got 42 kilograms. Kilograms to grams, right? Because we want kilograms to cancel. 1 gram is how many kilograms? 10 to the negative third, right? Which is the same thing as 0.001. So 42 divided by 0.001, what does that give me for my first answer? 42,000, right? Do we agree? Now we're going to convert grams to milligrams. Grams on top, grams on bottom, milligrams on top. 1 gram is equal to how many milligrams? 10 to the third, or 1,000. So I'm adding 3 more zeros, right? So that would be 42 million. And then we're going to write that in scientific notation. So that's 4.2 times 10 to the what? 1, 2, 3, 4, 5, 6, 7. And my unit would be milligrams. Do we agree? 4.2 times 10 to the 7th. Sorry. Any questions on number 9? All right. Unit conversions are something we did very early in the semester. So if you've forgotten all those prefixes, it's a good time to go back and review. Okay, let's decide if an orbital will form, and if it does, what will it be? N equals 0 and L equals 1. Is that allowed? No, that's not allowed. Why? No orbital. Because why? N cannot be 0. Why can't N be 0? L can be 0. How come N can't? That's its size, right? That's its size. That's its radius. You can't, if I say draw a circle with a radius of 0, all right, I just did, right? Because there's nothing to draw. N can never be 0. N equals 4 and L equals 3. Is that allowed? Is that permissible combination? That is. What's the name of that orbital? Let's review. L has shapes S, P, E, and F. Values 0, 1, 2, 3. So what would this be? 4F. Are you responsible for drawing an F orbital? Okay, let's talk about flame tests. You actually did flame tests in lab. That was an experiment you did. You did it early in the semester, so it's a nice time to review. What did you do? Someone refresh my memory. What did you do? You took your sample, and what did you do? Eat it? Hope not. What did you do? It turned colors when you did what to it? We didn't burn it, right? Because burning is combustion, right? We didn't set it on fire. Remember, a lot of you lost points in your report for that, right? Because we're not burning it. We took our Bunsen burner. There's our flame. We took our sample on a stick, and then we shoved it into the Bunsen burner, right? We did not actually ignite it. We just got it hot, right? It was not a combustion. And then what happened to the flame? It turned green or blue or purple, bright pink, orange, and then you had to identify some unknowns, right? That's what we did. So we added energy. We added heat too, right? That flame's hot. That's energy. And what did that do to the electrons? It excites the electrons, right? And so when an electron gets excited, what happens to it? In terms of atomic theory, what happens to it? That electron energy level, does it go up, down, stay the same? What? Goes up in the energy levels. But can it stay at that high energy level? No, it can't, right? So what happens to it? The electron, it falls back, right? Falls back down to wherever it was originally. And in the process, we get that energy back in the form of what? Light. That's right. Gives energy back as light, which we could see, right? That's what we were seeing. And each light has a wavelength. Remember, we did, I gave you the table of wavelengths, and I said, okay, this is blue, this is green, this is purple. Which color corresponds to this wavelength? Do you remember doing that? Those were post-lab questions. So that's what happens in our flame test. That's a fun experiment too, isn't it? Nice and pretty. And then you identified some unknowns. Remember, we had 2 you had to identify. Any questions on 11? All right, let's do 12. How many electrons are we dealing with here? Germanium. 32. I said do the full one. So you got to do the full one. All right, so all my little superscripts need to add up to 32. So we're in 4P2. All right, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p2. Do we agree? I did mine off the periodic table. That's my preferred method. If you prefer to use the diagonal rule, awesome. Okay, I have no problems if you do the diagonal rule. Just remember how to draw it. Okay, and if you use the periodic table, awesome. Just remember where the P block, the D block, and the S block are. I'm not going to make you go through the F block. Any questions on 12? Full electron configuration. All right. Let's move on. More math. Everybody's favorite. This time we're multiplying and dividing. So what's the rule for multiplication and division in terms of significant figures? Least number of total sig figs. All right. So my calculator doesn't know anything about sig figs. It's not that smart. So I punch it in, but it doesn't know how to round it for me. So 27.3 times 15.63 divided by 1.85. My calculator is going to give me a monster number of decimal places. 230.6481081. I have had students write this as their answer and then be subsequently sad when I don't give them full credit, right? Why can I not keep all these sig figs? Because this answer is obscenely more accurate than the numbers I began with, right? Your computed value can never be more accurate than the numbers that were used to compute it, right? You're only as good as your worst measurement. So how many sig figs can I keep? 3 sig figs. So what would this be? 231. Now again, if I'd given you units, you would need to carry those units through as well. Questions on A. We always round to the number of sig figs at the end, right? We don't round to 3 sig figs here and then divide and then round to 3 sig figs again. We always round at the very end. Sure.
I'm just like on the first exam, it's like whenever you add or subtract like grams and milligrams, do you have to make them the same?
Yes, yes. So if it was 5 milligrams minus 0.5 grams, which would give you a negative number, right? So maybe we should do it the other way around. You would need to make those the same units. Yes, absolutely.
It doesn't matter which way we do it, though, like if we go from grams.
Well, if you did milligrams minus grams, you get a negative number. So I wouldn't give you milligrams minus grams. But if I say grams minus milligrams, you need to convert this to grams.
Okay.
Or convert this to milligrams. Either way. They just need to be the same. Yep. That's a good question. All right, let's do this one. 130 divided by 18. Oops. Shoot. 130 divided by 18.02 times 2.641, close parentheses. My calculator gives me 2.76300514.6. How many sig figs can I keep? 2 sig figs. Because why is this number only got 2 sig figs? Because that 0 is not significant because there's not a decimal place, right? So my final answer is what? 2.8. All right, last problem. 12.24 times 6.2 divided by 17.29 times 3.1. My calculator says 1.415847311. Way too many sig figs. How many can I keep? 2. So what's my final answer? 1.4. Remember, always round at the end. Okay, don't round here and then divide and round again, right? Because that's going to give you a rounding error. Carry out extra decimal places, or if you can just enter the whole thing into your calculator using parentheses, then you just get one answer that you only have to round once. Okay, we only round one time. Questions on number 13. All right, let's talk about solids versus liquids versus gas. So in the solid state, you could have drawn it a couple different ways. You could have drawn it like a ball and stick model, right? We want to show that regular repeating arrangement. What's that regular repeating arrangement called? Crystal lattice, right? Crystal lattice. So you could have drawn that, or you could have drawn just a whole bunch of them together, right? That's like a space-filling model. And we need to show that they are in motion. What kind of motion do you have in the solid phase? Just vibrations, right? So just pick a couple of them and draw some little waves. Right? Vibrations only. All right, in the liquid phase, what do we have? They're more apart. There's no repetition, it's random. If you want to draw it inside a container, that's fine. And what kind of motion do we have? Small arrows, right. And pointing in random directions. And then in the gas phase, what does it look like? I'm going to draw this one in a container just for ease. Big, far apart, right? Big arrows. Nice straight arrows too, right? Do we agree? Questions on 14? Okay. Let's do 15. Let's make this, I can actually write in. There we go. Oops, make that font a little bit bigger. That's what I was. All right, that's better. Let's do this chart, something from the beginning of the semester. What element is this? Manganese. Has how many protons? 25. All right, that's the bottom number. How many neutrons? 30. How'd you get that? You just subtracted. How do you get electrons? It's the same, right? This isn't an ion. Right? If this were an ion, we'd have to add or subtract, but because this isn't an ion, just use the same as number of protons. And then for hyphen notation, you'd write manganese what? Is it the mass number or the atomic number? Mass, right? How come it's the mass number? Because if it were the atomic number, you wouldn't be able to distinguish between isotopes, right? Because they'd have the same. So, for instance, think like carbon 11 versus carbon 12, right? They have the same atomic number, different mass numbers. That's why I use the mass number, so you can distinguish between isotopes. All right, let's do our nuclear symbol first. If we know this, we know everything else we need. Because that goes on bottom. What goes on top? Well, first of all, what element is that? What's element number 50? Tin, which has what symbol? SN. And what goes on top? We round to the nearest whole number. It's like 118.7, so what would that be? 119. So now we can do the rest. This is tin. It would have how many neutrons? 69 and 50. Do we agree? Do we agree? And then it would be 10, 119. Questions on 15? Questions on 15? All right. The mass of a cube is 112 grams, and one side has a length of 2 centimeters. What is the density rounded to the correct number of sig figs? So this is a cube. That means that all 3 sides, length, width, and height, they're all 2, 2, and 2 centimeters. So how do you get volume of a cube? Right, so it's just be whatever this is, cubed. So 2 cubed. So 2 times 2 is 4, times 2 is 8. And this is centimeters. So what's my volume going to be in? What unit? Centimeters cubed. A centimeter cubed is the same thing as what? 1 centimeter cubed is the same thing as 1, who remembers? Same thing as 1 milliliter, right? So if that centimeters cubed bothers you, you can change it to milliliters. They are the one and the same. But that's only volume. The problem asks for density. What's the formula for density? Mass over volume. So I told you the mass of the cube is 11.2 grams, and we just calculated the volume. 1 sig fig, because this only has 1 sig fig, right? So how many sig figs are going to be my final answer? 1. So 11.2 divided by 8. My calculator says 1.4, but I can only keep 1 sig fig, right? Because that's got 1 sig fig. So it'd be 1, and then my unit would be grams per centimeter cubed, or I would also accept 1 gram per milliliter. I'd accept both. Questions on 16? All right, let's do 17. Heterogeneous versus homogeneous. What's the difference? Right, even distribution is in the homogeneous mixture, right? So it's even throughout distribution versus uneven. Because a mixture is just 2 or more substances physically combined. So, Powerade, either the mix or the prepared beverage, once you dissolve it, it would work either way. Would that be heterogeneous or homogeneous? That would be homogeneous. I should probably put the little trademark, right? It's a registered trademark. Got to be correct. Cereal here, heterogeneous or homogeneous? That'd be heterogeneous. Tap water, we talked about this one. It's heterogeneous, right? What about air? We talked about this one too. It's also heterogeneous. It's very close to having even proportions, but we can't say it's exact. Brass, which is an alloy. If you're looking at a brass doorknob, can you see the copper part versus the zinc part? No. So what would that be? That would be homogeneous. Potting soil, that's heterogeneous. Jello, either the mix, correct, right? Either the mix or the prepared product, assuming you don't put like fruit or something in it. What would that be? That's homogeneous. And then salad, that's heterogeneous. Questions on 17. Okay, 18 is a density calculations. What is the mass of an object that has a density of 1.536 kilograms per liter and a volume of 78.42 liters? So we're using density again. Density is equal to mass over volume. So we're just going to plug in and do some arithmetic. 1.536 is equal to m over 78.42. Right? So to get 78.42, and to get mass by itself, we're going to multiply. So mass is equal to 1.536 times 78.42. 1.536 times 78.42. My calculator is going to give me a zillion sig figs. How many can I keep? This one's got 4. This one's got 4. So my final answer is going to have 4. So that'll be 120.5. And what will the mass unit be? It's not grams. It's kilograms, right? Because the mass is in kilograms and the volume is in liters. So that means my mass is in kilograms. Also, another way I could trick you, because I'm a sneaky person. What if I said, and a volume of 78.42 milliliters? Ooh, I'd be sneaky and mean to do that, wouldn't I? The volume needs to match the volume and the density, right? So if this was in milliliters, you would need to convert that to liters so that it would match. Okay. Questions on 18? Everybody good on 18? All right, almost done. We got 2 more to go. 19. Why does ice float on top of liquid water? Why does ice float on water? Why does anything float on anything? Right, floating results when something is less dense. Right? And if ice is floating on top of liquid water, that means that ice is less dense than H2O liquid, right? So if we were drawing the particles, here's my, well, let's make my glass a little bit taller. Got a glass here, and here's the liquid, and here's my ice cubes floating, right? If I could see the particles in the solid phase are more spread out. It's like a hexagon. Whereas the particles in the liquid phase are pretty close. All right, so the particles are closer together in the liquid phase than they are in the solid phase. And that is abnormal, because most substances, when they become solid, get closer than in the liquid. However, water is an anomaly in that regard. Remember we talked about how water is a really strange substance all semester? Well, that's one of the anomalous things about water, is that it's actually less dense in the solid phase. You take the same mass and you spread it out over a larger area, its density is going to go down. Okay, last one. Classify as either chemical change or physical change. Evaporation, is that chemical or physical? Physical, that does not change the bonding, right? Burning, chemical or physical? That one's chemical. Melting, chemical or physical? Physical, right. Melting is a physical change. Neutralizing acid, chemical or physical? Chemical. Now let's be correct here. Registered trademark. All right, any questions on the review problems 1 through 20? All right, I'm going to stop the recording then.